Okay, so welcome to the afternoon session. So I believe that the tutorials are even more important than the lectures. So it is the time to play with codes. There are notebooks that the tutors will go through with you, and make the most out of these two tutorials that we're going to have today. The first one will be on the introductory material on machine learning that Fabian discussed. So Callum from Virginia Tech will tell us how to use machine learning, the rudiments of machine learning. Yes. Thank you.
Cool, thanks. Can you guys hear me at the back? No, not really. Yeah. Yeah, it is. Okay. Is this better? Is it a bit louder? Okay, cool. All right, so yeah, welcome to the first tutorial. So if you haven't already, you can bring up just on the website for the summer school. If you go to materials, then all you need to do is click this link here. So this whole tutorial will just take place in this Python notebook. And if you click on this, it will take you to Google Colab. So this was like option 2 on the website, which means all you need to do is have a Google account, and then you'll be able to use Google Colab. And I designed this notebook basically to be for self-learning. So you can just go through it yourself. You shouldn't actually need very much, but I'll try to explain things or stop occasionally to talk through bits that people aren't understanding or whatever. So the first thing, I guess, is just to make sure that everyone has something set up so that they can use something in the tutorial. So maybe if we can just take like 5 minutes, everyone try to make sure they've got everything set up. If anyone can't set something up, put your hand up. And I can come around and get either Google Colab working or something locally on your computer working. Has anyone had any problems, or has everyone managed to set everything up? Okay, good. Yeah. For this, you don't need TensorFlow, you'll need PyTorch. Yeah, so if you're running locally, if you're using this notebook, everything that you'll need, it'll be installed as you go through. But if you're running locally, what you'll need is PyTorch, Matplotlib, and NumPy. Cool. I don't know if the other guys are planning to use PyTorch or TensorFlow. We'll see if this one's going to be in PyTorch. Cool. Yeah, so if you're not already familiar, this is what's called a Python notebook, which basically makes the first part of this Python notebook is an explanation of what this is, how to use it, how to work with one. So we're using Google Colab, which is one of the possible online interfaces. There are other ones like Kaggle notebooks. Jupyter is something you can do locally. So if you're just running it on your own computer, you can just install Jupyter. And then additionally, when you run a Python notebook through one of these browser platforms like Colab or Kaggle, not only are you running something in the browser, but any code you run is happening on that computer that Google has or that Kaggle has. So you don't need to worry about having anything set up on your computer. If you're training a machine learning network, it's done on their computers. One nice thing about that actually is that it means that if you want to train with a GPU, so Fabian mentioned that training your networks on a GPU can be much more efficient. That can be a bit fiddly to set up on your own computer, but here it's really simple. I explain it further down in the notebook, but basically if you go up to runtime and you say change runtime type, then you can choose a hardware accelerator like a GPU. There's also a TPU, but we won't really talk about that. And then if you do this, you'll be running on a GPU. As I explained down below, you have to tell PyTorch to use it. And second thing is, if you are using a GPU and you're just using like a free Google Colab account, then there's a limit on how much GPU time you can use. So you want to like disconnect your runtime when you're done. Okay, so yeah, if you're not familiar with Python notebooks or any of the things I'm saying, then please read through this first part of the notebook. And then, yeah, the next part is about building neural networks with PyTorch. So this is one of basically 3 platforms that you might use for machine learning. One is TensorFlow, one is PyTorch, and more recently there's something called JAX. I think PyTorch is becoming much more popular than TensorFlow, at least in like an academic setting. If you look at how many papers are being written with PyTorch, it's much more now. And JAX is becoming more popular just quite recently. So yeah, you should just be able to import everything you need. And then we're just going to build neural networks in PyTorch in the simplest possible way, which is with this thing called sequential. So yeah, maybe the first thing I would say is if we could just go through this and people could try to set up, see if this code can work and see if you can understand how to write your own little sequential neural network. Maybe if we just take 5 minutes to do that, and I'll check back in. Yeah, and I guess just put up your hand if you want to help, or ask the people next to you. Probably they'll know something. The function?
So for this example,
yeah,
write it on the board.
Is in draw the network.
The network, yes, and then proposition a function.
One of these questions is like, what is the network? Like, figure out what the. I think we wouldn't figure it out. Okay, so hopefully you guys managed to get stuff set up, but I'll keep coming around in case you haven't. There was also just some more information, that's things that didn't quite maybe get covered so much in the lectures. Stuff like, which you might come to, stuff about, if you're interested, supervised versus unsupervised learning, classification and regression tasks. A bit more about what it is to train your model versus like checking the model's performing well, which means not checking it on the training data because you might overfit your data, which is something Fabian mentioned. So there's a bunch more information about that. Little questions to make sure you understand the concepts. So yeah, I guess if you don't know how this stuff works, please read through this and try to answer the questions. And then yeah, once you've done that, we go on to a bit more of PyTorch, actually train the neural network. So there's this stuff here about using the GPU, which again, if you haven't got to work, I can come and help you because that can be quite a nice thing. Yeah, okay, so hopefully you're still going on with this. And then if all of this is easy, you can jump more to using PyTorch functionality, these things called data loaders, and choosing optimizers. And then we'll get, at the end, we get to an example of actually building and training an image classifier. So depending on how easy things are for you, you might be able to jump ahead. But I'll keep coming around and seeing that people are making it through these parts. Okay, so maybe hopefully people made it through like a decent amount of the notebook now, but maybe in the last part, I'll just go through this last part at the end, which is this image classifier example, so that at least if people didn't get here as well, they can see how it worked, or if you already did it, you can have a think about it again. All right. So yeah, if you made it, if you looked through the notebook up to this point, you hopefully know how to build neural networks with PyTorch, simple ones, and to train them. And then the last part of the notebook was about doing this as an example. So in particular, we want to build a neural network that takes images of handwritten digits and then classifies them 0 through 9. And yeah, we want to train a network to perform this task. So this is supervised learning and we're going to use a small neural network. This is a classic example of supervised learning. The classic data set of handwritten images is this MNIST database. So you'll probably hear about that a lot if you look through introductions to machine learning. And this is one of the data sets where PyTorch has built-in functionality. So we can just download the data set for us. So that's what I'm doing here. Here I'm setting up a training set and a validation set by just grabbing it out of the list of data sets that PyTorch has. Yeah, one of them we're going to use for training, one of them we're not. This just sends this image data to a tensor, which we'll be able to pass into our network. So we'll see exactly what kind of tensor that is in a second. So we can have a look at the structure of this data that we've downloaded. So the individual elements of these images of handwritten digits. So we can take a look at the 0th element in the training set, which is a 5. So these are grayscale images. They're not in color. So each pixel just has like an intensity, and it's 28 by 28 pixels. And in particular, it's encoded in a tensor, which is 28 by 28. And this 1 is the fact that this is a grayscale image. So there's only one intensity, one number associated to each pixel. And then the labels for this data set, we can just pull out by asking for the classes. And the possible classification is 0 through 9. And then if you've read up to this point in the notebook, you know that we can batch our data and prepare it to pass into the training, get it ready for training with these data loader functionality, which is in PyTorch. So yeah, if you haven't read up to here, I guess Fabian already talked about often your data set is too big or to even put on your computer, and there are other reasons as well why you might want to just chop it up into pieces, which are called batches. Here we chop our data set up into pieces, which are 64 elements in each. And then this data loader is what's going to load that data into the training process. So here's a batch of numbers, 64 different handwritten digits. And then, okay, so that's the data step. And then what we want to do is make a neural network that has the ability to perform this task to classify these images. And we do the simplest thing, which is we use a single hidden layer. You could do obviously much more complicated things, but for this kind of problem, this is plenty. Yeah, often in the context of image recognition, you'll use what are called convolutional neural networks. Those are the state of the art for image recognition, really, but we don't need this. This is a simple enough task that we really don't need these. We can just do a standard linear layers feed-forward network. Okay, so there's some questions here which you can maybe try to answer, but so we can choose, okay, so we have a single hidden layer and we have an input layer and an output layer. The number of nodes in the input is fixed by the dimension of the image. We're passing in each pixel intensity, so however many pixels we have, that's how many nodes are in the first layer. And the number out is the number of possible classes that we're able to classify between. So the only thing we can choose is the number of nodes in the hidden layer. So you can choose all kinds of different things for this and see how it performs. You can think about what kind of numbers make sense. So that's what some of these questions are if you haven't already looked at these. About, does it make sense to have, say, fewer nodes in the hidden layer than in the output, or more nodes than in the input? So hopefully, if you try to understand these questions, you'll get a bit more understanding of what the hidden layer is doing. Okay, I should have coded this up before because now I don't know what I'm doing. Okay, so yeah, this is where we would define our sequential model now, which was, hopefully, if you've made it through the notebook at all, you know what the sequential model is doing. Yeah, okay, so I'm not going to code this up because then I have to go back and grab these pieces. Oh, maybe I will. Okay, so the first thing we need is a linear layer, a linear operation which takes us from our input layer to our hidden layer. So we started with num in, this guy, many nodes, and we're mapping to a layer that has num hidden, many nodes. People have already complained about me putting the comma at the start, so don't need to complain again. And then I think I said we should use a ReLU operation here. Is that the right syntax? Is it written like this? Cool. Thank you. And then, all right, that's the activation on the hidden layer. And then we need another linear operation to take us to the output layer. So that goes from num hidden nodes to num out. And then in this case, we don't need to apply anything like an activation layer at the end. Basically because we're already using this loss function called cross entropy loss, which is already basically applying a softmax function. There's some more information about this type of loss function because it can be kind of confusing. Okay, so we can set up this model. Oh, let's do it. No, I didn't run this. Good, okay. All right, and so here we're setting up, so if you read the notebook, I talked about different kinds of optimizers, which are basically better ways to do gradient descent. The most naive way is just step in the direction of the gradient by a set amount and then keep doing that every step. But there are different kinds of optimizers you might use. Here we're using something called the Atom optimizer, which is much better than naive gradient descent, but it's still doing gradient descent, but it's doing it in a smarter way. And the learning rate is basically how big of a step we take. Okay, and we set up the loss function. And then up above, we set up this training loop and this validation loop, which maybe you went through and hopefully you understood the steps. If you didn't, I can come around and we can talk about what this is actually doing. But yeah, so the training loop is where we're training our model. And then after each epoch, which means after we've gone through a whole set of the training set, every batch once, we check how this thing performs on the validation set, which is crucial. We don't want to check how it performs on the training set because we might have completely overfit the data. And so it's not at all a good representation of how well this thing generalizes. But yeah, hopefully if you get up to this point, you can train your network and it shouldn't take too long. I mean, there was parts in the notebook about using, oh, that didn't work at all. Well, let me finish what I was going to say, and then I'll look at it. Yeah, so I didn't actually go up and run through this notebook. So I talked in the notebook about sending things to the GPU or leaving it on the CPU. But this actually, it wouldn't really matter. You could leave everything on the CPU, and it's a simple enough problem that it's going to train pretty quickly in a minute or two, I think. And GPUs only really kick in for like quite big models, bigger than this one. But if you train this, and I'll try and fix this in a second, you should be able to get like 95% accuracy, which means, or more, which means 95% or more of the images were classified correctly. Maybe you also read the part in the notebook about why accuracy is different from like the loss function and why it makes sense to have both and not just read off what the loss function is doing. So yeah, hopefully you manage to train this and you can play with different numbers of hidden layers, or if you're interested, you can try different architectures as well, I guess, not just a single hidden layer, and see how it performs. So I'll let you do that if you haven't already in a second, and I'll come around. You also might wonder whether, I mean, people talk about these networks sometimes as being like a black box and you don't really know what they're doing. And to some extent, that's true. But in the case of image classification, when you have a bunch of these layers in your network, typically what's happening is, the way to think about it is that each layer is kind of extracting some kind of feature. Maybe the first one is extracting like line segments, if there's lines in the or corners or something in the image, those parts of the neurons will light up. And then maybe the later layers are sort of extracting higher and higher order features. Maybe it will start to look like faces or something by the end. Yeah. So if you want to find out a bit more about what these different layers might be doing, here's a little video which is quite nice, pretty introductory video. Here's this paper that I think was basically the first one to really talk a lot about interpretability of what these different layers are doing. Maybe we'll have a look at that actually. Yeah, this will just take a second. Or never come back. Okay. Well, if I can't look at this, then you should look at this yourself. Does anyone have a problem, by the way, that I can come and get you in a second when I've shown this? Does anyone want me to come and help fix up something? Yeah. Oh, cool. Okay, I'll go in a second. Great. Yeah, so there was some. Yeah, so I had some questions in there about what might make sense. I guess in some sense, lots of different choices would be fine. But yes, let me ask maybe would it make sense to have more layers, more nodes in the hidden layer than in the input layer? Does anyone have an idea of, if I had like 20 nodes in my input layer and then like 1,000 afterwards, anyone have an idea of whether that wouldn't make sense? Yeah, why not? Yeah, you basically, yeah, I think you would just be, there isn't that much information in your 20 nodes, right? You'd just be, yeah. You shouldn't go up after input layer because, yeah. Yeah. So, yeah. Yeah, I mean, I guess what you said, yeah. So in general, you might want to, because, I mean, I think I said sort of what is the interpretation of this. I didn't want to say it was the wrong thing to do. You're essentially just encoding information, right? When you do that, you're saying that this information can be encoded in a smaller dimensional space, basically. So, for example, when you're doing like language translation, that is certainly what you're doing. You're like encoding stuff into a small, so yeah, it could be perfectly sensible. And it would just be shame that there actually isn't like 10 dimensions worth of information. Anyway, so you can have a look at this paper yourself, but this was talking about, this paper was looking at what the different kind of features are that these different layers are picking up in an image. So this is like the activation of some neurons at the first layer, second layer, third layer, and so on. So I'll let you have a look at this, but you can see that sort of maybe layer 3 seems to be picking up these like interesting types of patterns that might appear in your image. Oh yeah, and in color is then the images that sort of made those things light up. So in the grayscale it's not quite grayscale, but these ones are how the neuron activations looked, and this is like the images that made them light up. Yeah. Yeah, this has no. Good question. I don't know the answer to that. Yeah. Yeah. And I mean, obviously in the network we made it have like one hidden layer. There's probably not a lot of information if you have a look at. Okay, anyway, so hopefully you can get through that example at the end. If you're interested, there was a few things in the notebook that pointed you to more information. So hopefully this, yeah, there's something for everyone to have a look at. But I'll come around now and see if I can help anyone out. Cool, guys. Thanks a lot for coming. Anyway, that's the end of the tutorial. It's a break now, and we come back at what time?
Yeah, so we have a half an hour break now. There is coffee outside, and we come back at 4 o'clock.
Managed to get through.